Rarely does a day go by that we don't, at some point, look at our own image in a plane mirror. Let's think about what properties these images have. First, the image is upright with respect to the object. In other words, when you look at your image in the plane mirror, you are not upside down. Second, the image is the same size as you are. Later on, we'll see that this means the magnification of a plane mirror is equal to 1. Third, the image is located as far behind the mirror as the object is in front. Notice that if I move closer to the mirror, my image, located behind the mirror, also moves closer to the mirror, thereby staying the same distance from the mirror that I am. Images in plane mirrors also have the following characteristic that we are all familiar with, and that is the image is reversed from left to right. Notice that if I wave at the mirror with my right hand, my image waves back at me with his left hand. Because of this characteristic, letters and words when viewed in a plane mirror are reversed. Here is a statement that appears reversed when viewed directly. However, when viewed in a mirror, it is easy to read. Let's now illustrate why the image formed by a plane mirror appears to originate from behind the mirror. Consider a small object sitting in front of a plane mirror as the figure shows. There are many light rays scattering off the figure in all directions. Let's look at a light ray that is leaving the bottom of the object. The ray travels from the object and reflects off the surface of the mirror. We draw in the normal to the mirror's surface and show that the law of reflection is obeyed, as the angle of incidence is equal to the angle of reflection. Our eye is at a position such that when this particular light ray strikes the mirror, it reflects along a path into our eye. As our eye extrapolates back along the reflected light ray, it appears to originate from somewhere behind the mirror, back along the dashed line. This locates the position of the point at the bottom of the image of the object. We can also look at the light ray that leaves the top of the object, travels to the mirror, undergoes law of reflection, and then travels to our eye. Extrapolating this ray back behind the mirror locates the point on the top of the image. Moreover, for each point on the object, there is a single corresponding point on the image, and it is this fact that makes the image in a plane mirror a sharp and undistorted one. Although the light rays entering our eye appear to come from the image, it is evident by the figure that the rays do not originate from behind the mirror where the image is located. Since none of the reflected light rays actually come from the image is known as a virtual image. We will always know that we have a virtual image when we have to extrapolate the reflected light rays back behind the mirror to determine the location of the image. We will see that when we study curved mirrors, there will be certain situations where the image is a real image. A real image is formed by the intersection of the reflected rays in front of the mirror, and no extrapolation back behind the mirror will be necessary. We can now use the law of reflection to prove one of the properties of plane mirrors, which is that the image is located as far behind the mirror as the object is in front. In the figure, an object is at a distance dO and an image at a distance dI. A ray of light leaves the base of the object, strikes the mirror at an angle of incidence theta, and is reflected at the same angle. To the eye, this ray appears to come from the base of the image. For the angles beta 1 and beta 2 in the drawing, it follows that theta plus beta 1 is equal to 90 degrees, and alpha plus beta 2 is also equal to 90 degrees. But the angle alpha is equal to the angle of reflection theta, since the two are opposite angles formed by intersecting lines. Therefore, beta 1 is equal to beta 2. As a result, triangles ABC and DBC are identical or congruent, because they share a common side, BC, and have equal angles, beta 1 and beta 2, at the top and equal 90-degree angles at the base. Thus, the magnitude of the object distance, DO, equals the magnitude of the image distance, DI. By starting with a light ray from the top of the object rather than the bottom, we can use the same line of reasoning to show that the height of the image is equal to the height of the object.